Hello everyone. In this session we are going to implement half aggregation in libsecp 256k1 ZKP, or at least that is going to be our goal for today. I'm Jonas, I'm a Bitcoin researcher at Blockstream, and I invited my colleague Tim Ruffing to join me and prevent me from doing the stupidest mistake in this little pair programming session.
Hello.
The general outline of this is going to be, first we're going to talk about what half aggregation is, and we are going to agree on some kind of pseudocode for this, and then after that we are going to implement this actually in libsecp ZKP. So let's get started. First, let's look into and recap what standard signatures are. So signatures generally consist of three algorithms: a key generation algorithm that takes a secret key and outputs a public key, a signing algorithm that takes a secret key, a message, and outputs a signature, and a verification algorithm that takes a public key, a message, and a signature, and then returns true or false depending on whether the signature is valid or not. Now, with aggregate signatures, we would introduce an additional algorithm. Ideally, that is called Aggverify or Aggregate Verify, that takes a list of public keys and message pairs. So in this example, public key 1, message 1, and then pairs until public key n and message n, and a aggregate signature, and then returns true or false. And there's one simple solution to this, which is that we just say this aggregate signature is just the concatenation of all the individual signatures. And then we just iterate over all the public key, message, and signature pairs and check individually if they verify. But we could call this an aggregate signature, but this wouldn't make too much sense. At least we don't gain anything by doing that. So we have an additional goal here, really, which is that the signature should be short, at least shorter than this trivial solution. So note here that what aggregate verify here takes are different messages, M1 to Mn. And this is, at least in our terminology, the distinguishing features to something like multi-signatures or music, where the message being signed is just a single one. So you have multiple public keys and one signature and one message, whereas here we have multiple public keys and each public key signs a different message, and the output then is one single signature. Now let's look into Schnorr signature half aggregation. Okay, so here we have two additional algorithms to our standard signature algorithms, which is an aggregate algorithm that takes a bunch of signatures and outputs a single signature, and the verification algorithm that we've seen before. The scheme is called half aggregation because the size of the aggregate signature is half of the size of the individual signatures combined. So essentially what you're doing is you aggregate half of each signature together into a single element, and all the other parts of the individual signatures you just concatenate. One great thing about this is that this aggregation step is completely non-interactive. And what this means is that there can be signers, they have secret keys, they produce these signatures, and then there can be a completely third party which has nothing to do with the signers, who just takes the signatures that have been made by the signers and aggregates them without having to communicate at all to the signers. And this was proposed on the mailing list in 2017. Perhaps it was discovered earlier in a different context already. And there was a recent academic paper from 1 or 2 months ago by Chalkias et al., who looked at the security of this scheme and then concluded with a security proof. So there are some applications for this. One of the most interesting applications would be for block-wide signature aggregation in Bitcoin. How would this work? Well, you have transactions. Each input still has a normal single signature, as is the case right now. The miners would collect these signatures as they collect transactions, and then they aggregate all the signatures, remove the signatures from the inputs, and only publish a block with only a single aggregate signature. So basically, they remove the individual signatures from the transaction and instead stick one aggregate signature into this block, which then decreases the size of the block as a result. And okay, it has potential downsides too. I don't want to go into this really, just to show that this is not a magic bullet, because one of the downsides is that at least it destroys the naive way of doing adapter signature atomic swaps. But perhaps there's some ways to work around that.
Right, but if you look at it otherwise, if you forget about the downsides for a minute, this is like the savings here would be huge, right? You would save half of the signature per transaction in size.
Yep.
Which is like 32 bytes per transaction. So
yep.
If we can solve this adapters signature stuff, and if there are no other downsides that can be discovered, then this would be a great thing even on the Bitcoin main chain. But yeah, as Jonas says, this is let's say future stuff. We first need to solve a few other problems before we can do this.
Another application would be layer 2 gossip protocols. For example, in the Lightning Network, what happens right now is that the signatures, there are signatures basically proving that the parties sending these messages actually own channels on chain in order to prevent spam, etc. And since these on-chain signatures consist of Schnorr signatures, and perhaps the gossip protocol would want to switch to Schnorr signatures eventually, they could also save half of the size of the signatures in gossip messages by using this half aggregation scheme, which could be substantial. Okay, as an aside, there's also the concept of full aggregation. Put that in quotes because there's no real established name for this. And this would mean that an aggregate signature is just as big as a normal signature, which would be a huge improvement over half aggregation. But the downside here is when you want to do that, then the aggregation step really is interactive, which means that the signers need to communicate with each other to produce such an aggregate signature. And one application of this would be just transaction-wide aggregation, because for transactions, in most cases, there already is the assumption that all people participating in creating a single transaction already collaborate, and they could also collaborate and communicate to produce an aggregate transaction, aggregate signature. And this can, in theory and in practice, also be combined with half aggregation to get even more savings.
Maybe one additional thing to note here: if you say that this is interactive, then this is basically true for Schnorr signatures. So we don't have a full protocol yet, but it's conceivable that we can build a protocol that does full Schnorr aggregation, and this will be interactive. There are other signature schemes where this is even non-interactive. For example, BLS signatures that have been used in some other cryptocurrencies. This is all great, but they require different cryptography that we currently don't have in Bitcoin. So our focus here is just Schnorr signatures.
Yep. Okay, so now we want to create pseudocode for half aggregation. And before we do that, we look first into how normal Schnorr signature verification works as per BIP 340. So this is essentially the pseudocode from BIP 330, the pseudocode of the verification function, which takes a public key, which is a byte array, a message, which is a byte array, and a signature, which is a 64-byte array. How does it work? So I don't want to go too much into detail here. What essentially happens is that it parses the public key and the signature. So this public key is 32 bytes. So it interprets these bytes as an integer. And then from this integer, it creates a point on the curve by interpreting the integer as the x-coordinate of a point. And if that fails, because the x-coordinate isn't on the curve, then the whole verification fails. Then it parses the so-called R value from the signature, which is the first 32 bytes of the signature, interprets that as an integer, and verification fails if this R value is greater than or equal to the prime P, which is the field order. But that's not too important. We just need to remember that we need to fail at some point, also for half aggregation. And then it parses the so-called S value, which are the remaining 32 bytes in the signature. And it fails if this S value is larger than or equal to the group order. Then it interprets this R value as the x-coordinate of some point. If there's no such x-coordinate on the curve, verification fails. Okay, and now E is the so-called challenge hash. So this is just a hash function. Let's skip this for a moment. A hash function applied to these arguments here, which are the R value, the public key, and the message. And we take the result, interpret it as an integer, because the output of the hash function are bytes, raw bytes, and then we take that modulo the group order n. Okay, so what does this mean? This means simply that this is what we call a tagged hash function, so a hash function which has a specific state, which was produced by hashing just this string, for example. And the result is that if we use this tagged hash function as opposed to a hash function that is tagged differently, we separate these two invocations of hash functions, and we cannot mess up by mixing two different hash function invocations in two different protocols where they shouldn't be mixed up. So this is, you could call it, this is basically the name of the hash function. So now we check this verification equation. Namely, we multiply s, the scalar s or integer s, with the group generator G, and we check if that's the same as adding the R point with E times, where E is the challenge hash, the public key point. So if that verification, if these two things are not on the left-hand side and the right-hand side are not the same, then the Schnorr signature verification algorithm fails. Okay, so at this point we don't really care why this works, why this is secure, why this is correct. We just need to know that this is roughly how Schnorr signature verification works. Okay, so let's look into half aggregation now. Let me make this smaller. So what we see here, this is basically the main insight behind half aggregation. So the idea is, what if you just concatenate the R values of the individual given signatures and then just sum up the S value and take this summed up S value plus the concatenated R values as your aggregate signature. And this seems like a good idea, but it's actually insecure. Well, we don't want to go into why, but it is insecure. But a similar thing works, namely, we don't sum up the S values directly, but instead we sum them up after multiplying them with unpredictable values. Okay, so that's what we're going to do now. We have an aggregate function. It takes tuples of public keys, messages, and signatures, and will return an aggregate signature. So what it does is it basically iterates over all signatures. Wait, this should be sig I. This should be sig I. It iterates over all signatures and just parses or extracts the R and S values. Then it computes these unpredictable values, n many of them, call them Z. And again, we use a tagged hash function. And we basically hash all the values that we know so far, except the S values. So for each signature, we hash the R value, the public key, and the message. And we hash the index of this particular unpredictable value. And we interpret the result as an integer and take it modulo n. Then, instead of summing up the individual S values, yeah?
N is overloaded here. That's maybe confusing.
N is overloaded.
N is the number of signature, and we take the C mod N, but N is the...
Right.
It's a totally different N here.
Right. Do we do this mistake somewhere else? No.
Yeah. I mean, it's we have the mod N over there too. Maybe call it P or...
We could say we have M signatures. How about that? Just need to remember everywhere to change it. How about this?
Yeah.
Yeah, no? Oh no, M is already taken as well. Well, we'll leave it for now. And you just need to remember that this mod N is a different N than the number of signatures. That's the group order. Perhaps we should call it capital N. I will fix that later before
That's a nice
uploading
idea.
this. Okay. So now what we're doing, we have these unpredictable values, and instead of summing up the S values directly, which was our initial idea, we first multiply each of the S values with this unpredictable value. And each one with a different one. And then our aggregate signature is the concatenation of the individual R values that we've basically just extracted from the signatures and this aggregate S value. And that is basically it. Okay, so now how do we verify this thing? So the first loop, okay, aggregate verify, it takes, again, public keys and message pairs and an aggregate signature, and then returns true or false. The first loop here is we're iterating over all signatures and basically just parse the signatures as before. So that is very similar to normal Schnorr signature verification for each individual signature I. So we first, from public key I, we get a public key point I. We have to look now into the signature for a specific position of the ith R value, and then we call that thing Ri, and we compute a point from it. And again, if there's no such point, we fail. And for each signature, we compute this challenge hash, which is again tagged hash function, same as before. And we hash the R value, the public key, and the message, and take that modulo the group order. Once we have that, we can compute the unpredictable values again. And this is the same as in the aggregate function. It should be exactly the same. It must be exactly the same because we want to get the same unpredictable values. Then we parse the S value, the aggregate S value, from the aggregate signature. We just need to look at the right location again. And now we have this verification equation. So we multiply the aggregate S value, and then we check if that is equal to each of the individual right-hand sides of signature verification. Maybe I should here. Okay. So what we have is, for each individual Schnorr signature, we have that R plus E times P is equal to S times G. So this right-hand side of each individual signature verification is now already also represented here, but it is multiplied with unpredictable values. And we do that for every Schnorr signature that we get. So if the left-hand side here is equal to the right-hand side, then aggregate verify succeeds, which should imply that each of the individual Schnorr signatures are valid. Okay, now we can look a little bit more into just try out an example, perhaps. So we have two signatures, R1S1, it's our first signature, and R2S2 is our second signature. Then we compute an aggregate signature, which consists of both R values, so R1 and R2, and an aggregate S value, which is unpredictable value times S1 plus unpredictable value 2 times S2. Now, for our verification equation, our verification equation holds if, wait, this misses a G. Okay, so this is essentially the verification equation, where the aggregate S is now written as the individual parts summed, and on the right-hand side we see also the same as in our aggregate verify equation. This should be small r. And now, since we know that for each individual Schnorr signature, we have that because we assume that the given Schnorr signatures are valid, we have for the individual Schnorr signatures S1 times G is equal to this, because this would be the equation for our individual Schnorr signature. And now, since we multiply both sides by the same value, Z1, we know that if they are indeed our signature 1 and 2, if they are indeed valid Schnorr signatures, then this verification must succeed as well, and the left-hand side must be equal to the right-hand side. Okay. So we have that here, and from that fact it follows that this holds. And also the same, of course, for this holds for both our signatures. Okay. So now, I think we're done with the theory. We will need to go back to the pseudocode in order to be able to basically copy that and bake C code out of it. So our we're doing now is we're going to implement the aggregate and aggregate verify interface. Then we try to write a test for this. So just a simple correctness test, which means that we create a bunch of Schnorr signatures, we aggregate them, and then aggregate verify should always succeed. Then we can implement aggregate and aggregate verify, and pretty sure that we won't get to this. So I'm writing here bonus for another episode. We could write a test that somehow tries to test unforgeability, of course, only in a very broad sense, where we create a bunch of Schnorr signatures, we aggregate them, and any random bit flipped in the input of aggregate verify will make it fail. That is basically just a sanity check. We probably won't get to it today. And there's a bunch of other things that we can do. We could write a separate module for this, which we are not going to do right now. Write more tests, API tests. We could use multi-exponentiation in order to check this verification equation, which isn't very important for a proof of concept. But if you want to use this in practice, this would actually make this verification equation a lot faster. And there's also an optimization where you could set the first unpredictable value z to 1, which saves a scalar multiplication here. But these are details, so let's get started with writing code. Tim, are you ready?
Always.
Okay, so I have my checked out project here. That's just secp zkp. It's perhaps a little bit small, but I cannot change it, and we're not going to spend a lot of time in the shell anyways. But I'm just going to clean this, and now I'm going to start with the first step that you have to do if you want to use secp zkp. You have to run autogen.sh, which generates config and make files. Okay, now we can run configure, and we need to enable experimental because we're going to enable an experimental module, which is the schnorr-sig module. Okay, and then we run make to build this. All right. So this should build a bunch of things, like you see exhaustive tests, benchmarking binaries, and a test binary. So we can run the test binary, and just to check if our tests run, and this should take only a few minutes, and then we see if our master branch is fine. But in the meantime, I can open, I think, my editor. Oops, that's the wrong Bitcoin, secp, zkp. Okay, so I can start the editor. Okay, no problems found. That's good. So what we're going to do is we add these functions to the schnorr-sig module. And because essentially what we're doing is we are half aggregating schnorr-sigs. So
maybe you can increase the font size.
Right.
A little bit.
That's a good point. How about that?
That's good.
All right. Right. So these, I'm now in a file that is called include/sec p256k1 schnorr-sig.h, and this contains all the functions of all the public functions of the schnorr-sig module, which implements BIP 340. So there are a couple of things here perhaps not too important. You can create a Schnorr signature by calling sign. You can verify Schnorr signature. And that's basically it, because X-only keys are defined somewhere else. Okay, so what we want is a SegP256K1 Schnorr sig aggregate function, right? And it takes a context. Context CTX. Tim, what is the context?
Yeah, maybe let me explain while you type. Context is just a thing that you need to parse to every call in this library. The idea is that it has some pre-computed values that are used to speed up multiple elliptic curve operations. So this is just a standard thing that every API function takes, such that the function itself can make use of the pre-computation. And in beginning, as a user, when you use the library, you have to create a context, and you just take some time, then you can pass this context to every function.
Yeah. So in particular, this makes the what we call scalar multiplication faster, because you have some pre-computed points, like you have scalar x and like group generator g, then s times g would be scalar multiplication in our terminology, and that's faster with CTX.
X times g.
X.
Yeah. Of course, yeah.
And also it has custom error handlers, but I guess we're not going to get into this.
This is really the details of the library.
Okay, so what does it out? So first, the first argument is usually the context. The next arguments are then the outputs. And output is our aggregate signature, right? Exig.
Yep.
And since this is our output, do we also want to output the size of the aggregate signature, or do we assume that the user knows that? Perhaps we output it. I guess that's better.
Yeah, I guess because
let's make it even better. Let's make it an in-out argument. So you give it the size of the aggregate signature array.
Yep.
And then the function will set it to the actual size of the aggregate signature.
And of course, first check not to make sure not to override it.
Okay, so that is a pointer to a size type, and we call it exig size, perhaps. Okay, this is our output, and our input is, let's look into our pseudocode. So we need public keys, messages, and individual signatures. So what order does Schnorr sig verify does that? Okay, first the signatures. And these are unsigned char. Let's make it pointers to 64-byte arrays, or 64-byte blobs of memory. So this should be an... Okay, if you're not that familiar with C, what I want to express here right now is that this argument is an array of 64-byte characters, basically. Then the messages, similarly. I remove the const here for now. And although these arguments should be const. And then we have an array of public keys. I think that should be fine.
Yes.
For now. Okay, and what else? We want to have these macros here. I don't know exactly what this SegP256K1 API does. I mean, warn unused result. I think that's enables some compiler feature.
Yeah, so the API thing is really some compiler shit. I think that we for example, that it's necessary to make better binaries on Windows. It's really not interesting. I think the one unused result is more interesting. This tells the compiler that if a user uses this function and throws away the result, then it should warn the user about this. In that case, I'm not sure if we want to sign it. If we want to have it here, because it's the aggregation function. It's probably not too bad if you throw away the result.
Yes. How do we do it in signing?
Right, we don't, yeah. But you copy this from the verification function, and there we really want to have this, right? Because like usually if you verify a signature, then don't care what the verification result is. That's a mistake, and that's a huge foot gun, because then you could verify the signature and just still go ahead even though you had a verification failure.
Yeah, and in the meantime, somewhat similar, there are also these macros here, which will warn you as a developer if you provide a null argument at any of those argument positions. The index starts at 1 here. So this is actually for the context. And none of these arguments are allowed to be null. That's what essentially I'm trying to say here.
And they are all pointers, yeah.
Yeah.
Indeed.
Okay, so now we can create our SegP256K1 schnorr sig ag verify. Again, this takes a context. And what else? It just outputs a Boolean. So an integer in our case, either 1 or 0. 1, oops. So, and as inputs, it gets, I suppose, the messages, public keys, and the signature, I would say. So we can copy this over. Messages. Wait. Public key, and now we don't have an array of signature, but just a single signature, but that is our aggregate signature now. And we also need to tell this function how large the aggregate signature is, x6 size. All right. And again, we want to prevent user from giving null arguments. So 1 should be non-null, and messages should be non-null. Public key exit, yeah. So basically,
everything should be non-null.
So we have 4, 3, 2, 1, 2, 3, 4. Yep. All right. Let's check if this compiles. Projectile compile project make JA. No. Okay.
There's a comma missing.
There's a comma missing. No.
Yeah. I just wanted to ask why the syntax highlighting is different for Aggregate. Yeah, the comma.
Well, I don't trust the syntax highlighting at all.
Yeah. Right. Okay.
Okay, but that seems to work. We wanted to write...
At least the interface is syntactically correct.
Yeah. We wanted to write a test. So let's do that. We have in the... So the general directory structure is that the module is in src/modules, and there's a schnorr-sig module, but there are also other modules. And in this schnorr-sig directory, there's this main impl. This is where we're going to implement the functions themselves, so aggregate and aggverify. And there's also a test file specifically for this module. So let's go into that file. And here we have a function that just runs all the various Schnorsig tests. You can see here is an API test, and then there are the Schnorsig BIP vectors that are tested, and there's a taproot test, and here
the font size is again small.
Seems like I need to change it for every file that I open. Wait, if I open main Schnorsig, yeah,
I guess it's
the main files
going to the buffer. Yeah.
All right. So test Schnorsig aggregate. It's the function that we write. Can I make this a little bit smaller, like this?
Yeah, that's okay.
Test Schnorsig aggregate. Okay.
Void.
Void?
Yeah.
Void. Right.
Void. Twice, in fact.
Twice, in fact, because here we're dealing with C89, which has all kind of weird things. All right.
All kind of void things, even.
Let's copy this over, because that's what we want to do. And I learned this from you. So Shift-J in Emacs, as a pro tip, removes the new line.
I think only in evil mode, yeah. But yes.
Okay. All right, so our function takes a context, and in the tests we have a global context variable, so we don't have to deal with this at all, which is nice. Then it takes an AXIC array, so an actual aggregate signature. So we need to create it unsigned char AXIC. Let's make it empty for now. Let's see what happens. Okay, that's our AXIC array. And we need the AXIC size, so that's a size t. AXIC size is equal to size of AXIC. And we need to take the address of this. Now we need actual signatures, so we need to create them. Unsigned char sig 64, and these are like, perhaps we define n6, say we're dealing with 3 for now, and we have 3 signatures of 64 bytes.
Maybe then you should use the define.
Should actually use it. N6. And we need to create them as well. So we have a loop here. I smaller than n6, I plus plus, and then we have to create these signatures. How do we create signatures? Well, before we create signatures, we need secret keys. Do we need them again? I think we can create them in this loop here. So we have a sec key. Perhaps we even have a helper function in this file which helps us with creating such secret keys. Let me see. Let me look for it.
Yeah, I'm not sure, but I guess in the other tests, Schnorr test functions, we sure also need to create.
Perhaps it's in the extra keys tests.
Maybe.
That's small again, sorry. You see a lot of tests. I don't
sure
see
there are
it, but here I can
tests.
copy
Right.
something.
Yeah.
here.
Can also use the hard-coded test vectors, but I guess that's not so useful. Right. But the sec key is too long. Yep.
So from the secret key, we create a key pair, which is a data structure that holds both the secret key and the public key, and we're going to need that to create a Schnorr signature. We have not defined the key pair yet, so we haven't declared it, I should say. So here's our key pair.
Yeah.
Okay.
Yeah, and this test run function is a little bit special. That's that's just what we use in the test to create random data, and a secret key is just random integer in a sense. In a real in a real program, you would use another function, but in the test, this is fine.
And exactly this is why we call it test rand, because it's only supposed to be used in tests.
Is this the one that's biased? I don't know.
I don't remember.
Yeah, whatever. Doesn't matter. We have some. We have
it's
some
called test run test. No, test run test is the test of the test run.
Okay, yeah.
Test run int, test run bits, but yeah, we have some biased way, or a way to create biased 32-byte numbers, not uniformly random.
To test some special cases with higher probability. No, but in this case, the main reason to use this function here is that all the tests, all the randomness used in the test is created from a deterministic seed, such that if you have a failure, you can reproduce it later again or on a different machine. That's why we have our own random number generator in the tests.
Yep. Okay, so now we want to sign a message with our key pair. So we need to call the Schnorr-sig sign function. It takes a context. As an output, it takes a signature. So we already have these signatures here. That's signature I. And we need a message. We don't have a message right now. So we create messages in exactly the same way. 32 and 32 here, and we need to initialize them with some value. So MSGI.
Also sign the keys. If you want. No, but
yeah,
maybe a little bit dirty
key.
for the tests. Whatever. Let's do it properly.
And it takes our key pair, and these last two arguments we can safely ignore.
By the way, the check, I think we haven't talked about this one. This is just our test assert. Like this supports if this checks the condition in its argument and aborts the test for the failure if the condition doesn't hold.
Right. Okay, so we have signed now. Back to our aggregation function. We have signatures now. We have messages, but we do not yet have public keys. So we also need public keys. We only have a key pair right now, so I'm going to look into the extra keys module, how we get a public key from a key pair. And in particular, we want an X-only public key, because this is what our Schnorr-sig aggregate function wants. And here we have let's search for key pair. Key pair. A bit too big for me.
Get the next one.
Get
the X-only public key from
key pair X-only pub.
Yep.
We have, so we don't need the macros. We check the result again. It requires a context. it requires an X-only public key, which we have not yet declared. So let's do that here. We want N6 many public keys. So here's our pub key I. We need to take address, and we don't care about this argument. And this is our input key pair, which is just called key pair. Okay, and now, oops, and now we have a pub key, which we can, or after the loop is done, we have an array of pub keys, so we can provide it here. How does that look, Tim?
Looks okay, I think.
Should I
Don't
try
see
to
a
compile?
problem.
Let's try to compile.
If we don't,
Passing
the function is not
argument,
implemented.
incompatible pointer, unsigned char 64.
So when you say last time, there's a sad story about this video. That is that we recorded already, but somehow the recording didn't really work out, so we have to do it again.
Yeah.
But as you see, we still do the same mistakes again.
So I think one problem earlier was that I just changed the wrong function here. So 664 yeah, that should work, and these should be 664 pointers and message 32 pointers. So let's see if that now works. All right, I think that looks good. Yeah, so that's the expected error. Now for aggregate verify. So we look into
maybe remove the last call to make the error disappear, and then we see if this checks out so far.
Yep.
Okay, unused trivial. I see. But maybe we can see if the test pass.
Okay. So just to recap, what we're doing here is we generate here one large array of N6 signatures of 64 bytes, and then we basically create an array of pointers into that memory, such that we can give it as an argument to our aggregation function. And we do the same for messages. Okay.
But it means we have pointers to pointers now, right? In fact, yeah, and that's what we declared, yeah. Yep. Of course.
Okay. Now egg verify. Check. We check that this succeeds, and we give it a context. We give it our message pointers. We give it our public key array. We give it our exig, and we give it the exig size. Okay, let's see if that works. All right, we get the expected error. Okay, I think now we can start implementing.
Yeah, we haven't initialized pointer arrays, right?
Ooh. Did we not? Okay. Then let's simply do that. So MSG 32 PTRI is equal to MSG I. I think this should work. MSG 32. Okay, that looks good.
Yeah.
It's an error, but it's the one we expect. Okay, include schnorsig, and we are now going to implement this in our main impl file. So let's copy these two functions over. And remove all the boilerplate. And then we can start implementing return 0. And here we return 1. And we can make this unused parameter, which doesn't matter right now. But we can run the tests now. And now I think they should succeed up to egg verify, which should return 0. Okay, let's run the test in the background. Okay, now we're getting to the meat of it. Back to our pseudocode. I'm going to copy the pseudocode over. So, oops, that was too often. Okay, so we need to iterate over. Oh, we forgot to give both aggregate and aggregate verify the number of signatures. At least for aggregate, yep. We forgot that. So
right, for verify, it could be computed from the size. Not sure if we want this. Guess we want this. But yeah, we need it for aggregate.
I don't think we want this because this X6 size is potentially untrusted. I call this N6.
Yeah, sure, yeah.
And here N6, yep. Or N pub keys rather. Or let's call it N messages.
Yeah.
For the number of messages, and the same here. N messages. Okay, now we need to change that in the include file. And here as well. It looks a little bit random where it is right now. I don't like that. Let's call it N6 here. And here we can call this N pub keys. Let's keep with N messages. Okay, Or we could just call it n. The end.
Yeah.
So where did I put this now? And
The end.
6 here, this in the end.
That's also strange, right? Oh.
It's a bit strange, yes. Okay, so we want this loop now. So we have an I and we iterate over n6 and I is initialized as 0 and I is incremented by 1. Oops. Okay, and we have this. We have these RIs and SIs, and we want to hash them. I think we can do this in one step, and I think we also want to do this in one step. Okay, perhaps let's start with SI. So we have in libsecp we have this scalar type, and that is what is going to hold our SI. And we have a function to parse a 32-byte array into a scalar, and that's what we're going to use. And this function is, we can find that somewhere in scalar.h. And here we have a function, convert a scalar to byte array, no, the other one. Set a scalar to, no. We search set B32. Yep.
Yeah, that's right.
That's the right one. Our scalar is SI. Our binary byte array is sig 64 I 32. And we don't care about overflow. Overflow would be if the S value is larger than the group order. Then this overflow flag would be set to 1. Okay, and what we're going to do is we're going to initialize this hash function. And we're going to use SHA-256 because that's what we have available in libsecp. So there's this hash.h file, which has these SHA-256 declarations. So we will need initialize, write, and finalize. Copy them over. So first, we initialize. But for that, we also need to declare a SHA-256 state. Let's call that hash. And we initialize it. And we write into it. What do we write? We write the R1 value.
Yep.
And that's the first 32 bytes of each signature. So 64 I. And the first 32 bytes. Then we write the public key. So for that, we need to convert this X-only public key into, we basically need to serialize it. So we define some byte array, pub key or pk ser for serialized. And now we need to check how we can serialize X-only public keys. And again, this is in the extra keys.h include file. So let's search just for serialize. X only pubkey serialize, that's the one. Okay, so we've written R, now we serialize this public key, so we give it a context and we give it an output, that's our PK sir, and we give it the public key, which is public key I. And if that fails, we want to basically return 0.
Yeah.
All right, that's public key I. And
we
now
still
we
need to write it to the hash, right?
We need to write it to the hash.
Yep.
And the next thing that we write is the message. MSG 32I, and that is 32 bytes.
Yeah, it's easy again because we have it.
And now we are going to
after the loop we
need
the
to
index.
Yep, we need to write the index. For each zi, okay, I guess we need another loop to multiply. So that's going, where's the rest of our, okay. We need another loop to multiply the z values with some s. So this is where we can compute the z values actually. The final z values. Let us do that. Probably don't know what I mean right now, but I guess that will become clearer in a moment. So what we do now is we basically...
But you don't want to have the finalize call here?
We do because we use a different... perhaps we should copy... We should have multiple hash functions? No, because...
oh yeah, okay, yeah. I see now, yeah. So you just finalize this to different... finalize the same mid state to different...
Can't we multiply... Can't we compute the z value here and multiply it with s already? I think we can. Perhaps that's the easiest.
Yeah.
Let me try to rewrite this into a single loop. So we initialize s as 0. Then we basic. No, right. We need to. Sorry, I forgot. We need to do this differently because we need to write and write and write and write. So perhaps we finalize here to have like a, let's call this, so we finalize our hash function here and we write this into some intermediate hash.
Yeah, we can also do this. Yeah, or we could copy the mid state.
Yeah, but I don't want to copy the mid state really.
Yeah.
At least right now.
Yeah.
Unsigned char, and this is like, how do we call this? Mid hash.
Yep. So this is the hash of everything without the index, and then we create a second hash.
Yeah. So this is the hash of everything without the index. And now...
Also, we are ignoring the tagging of the hash, right? But
yep.
That's also
yep.
okay for now.
We ignore the tag completely.
Yeah.
So we initialize another hash, and now we write the index into it. So I think we can interpret the index just like this. Unsigned char. But size of we want to have a fixed size I in that case.
Yeah. But this is an endianness issue, right?
This is an endianness issue, yes.
But maybe put a fix me next to it then. Yeah.
So what we want to do is, can I write it like the size of I?
Yeah.
Okay, so what we want to do here is simply hash this index I. 32, it's 32 bytes. Okay, so we hash it, then we finalize again. And this is now our randomizer. Why do I write right? I want to finalize. Finalize into our randomizer. And our randomizer isn't declared yet, but that's again a 32 byte array. Okay, and now from that 32 bytes, we need to create a scalar such that we can multiply it with each individual S value. So again, we will use scalar set B32. Here, call this thing ZI. Sec P256K1 scalar ZI. And ZI is set to the randomizer. And again, we don't care about overflow. I think I need to take address everywhere here. Yeah, I see my comments here are all over the place and not very helpful. Let me clean that up. Okay, we don't need to have this comment because we know what a loop is. And so this is basically this part. We're setting SI to some part of the signature. And we try to compute ZI. I'm going to put this perhaps somewhere up here to demonstrate that basically this applies to this whole function. And so we write pkser, we finalize the thing, and we don't need this. And now, right, we compute the summed S value. We have the randomizers now. So let's multiply the individual SI values Wait, we don't need to parse the SI values here because we don't need them. We don't hash them. We only hash the R values, the pub keys, and the messages. You can see here. Do we do that? R values, pub keys, and we forgot the message. Ha. So message 32I.
Right.
I thought we did this somewhere.
Right. Maybe you removed it by accident. Pretty sure we had this.
Yeah. Okay. We said Zi, we set Si. Now we can multiply CS, Zi and Si. And again, we look into the scalar header and look for a multiplication function. Scalar mul is what we want. So this function multiplies A and B and stores the result in R. So we store the result in Si and we multiply Si with Zi. Okay. Now we want to sum up all these individual values, and we do that by initializing some, declaring some scalar S. And we call segp scalar, how is it called? Segp scalar clear to set it to 0.
No, I think we should call set int and 0. And maybe currently clear works, but the goal is that the clear functions just nuke the value, so they overwrite the memory with nonsense. And nonsense currently is 0, but
this is news to me.
Yeah, this is after my PR upstream is
okay.
rebased and merge.
I think we use clear a couple of times exactly to set it to 0, right?
I think there is
okay, the documentation is already reflects what you're saying.
Yep.
Set scalar to unsigned integer. Okay, so that's what we're doing. We set it to 0. However, some additional argument. We need the argument S, and then we can use scalar add S Si. So we add S and Si and store the result in S. Okay. Now, so one thing that we should do is, so what we want to do now is we write the result into this exig array. So what we should check first is that the exig is large, exig array is large enough.
Right.
And also we forgot all the arg checks and contact and verifies.
Yeah.
So let's perhaps do that now. Let's do the more interesting thing now. So what we do to check, should we do that as an arg check or not? Perhaps let's not do it as an arg check right now. So what, the exig size check.
Yeah, no, this shouldn't be arg. I don't know. Yeah, let's not do it for now.
So what we want is, so the output is, we have one 32-byte element, so we have 32 times 1. That's the S value. And then we have N6 many R values, right? And yes. Each of them is 32 bytes. That's what we're going to return here. So if exig size is smaller than that.
Yeah, but exig size is a pointer, right? So we first need to arg check it for null.
If exig size is smaller than that, then we return 0 because then we cannot aggregate.
We need to see if this should be an arg check or not.
What we want to check is exig size null or not? Because if it is, we need to return, and we usually do that with an arg check.
Arg check is a macro that if the check fails, basically aborts the program.
Yeah.
The idea here is that this is an arrow that we always want to, where we want to fail pretty hard. because this indicates really a bug in the caller code and not just a runtime failure. And of course, if you pass a null there, this is a bug in the caller code. If you pass the wrong size there, I'm not sure if this should be considered a bug in the caller code, and we may need to look at other functions in the library to see how they do with such how they deal with such size arguments.
Yep. And one thing that argcheck actually does is it doesn't necessarily fail hard. It calls the error handler in the context object, right?
Yep, which defaults to failing hard, but
yep.
can be changed by the user. Yeah.
But what this means is that we cannot argcheck the context object itself, because it cannot we cannot call an error handler on something on a null pointer. So we use this verify check here, which
and
will also abort
check
hard.
Just but only in the test.
Yeah.
So if you could also use check, this will also abort hard in user programs, but we don't do this because So I mean, if your context is null, you will figure out pretty quickly, because then every API call is probably a segmentation fault or undefined behavior. So we leave that part to the user.
Yep. Okay, so what I'm doing right now is I'm setting the exec size. And now we can basically, let's see, perhaps we want to do that before and already copy in this loop, copy over the R values. So we copy into exec I times 32, we copy sig 64 I the R value, this, and 32. Is that correct? We have some pseudocode here. I think it looks good. So what we're doing is we copy the R value of each signature, which are 32 bytes, into our exec array, and we already know it's large enough to hold it. And
yes.
What we now do in the end is, instead of setting a scalar to a 32-byte array, we do the opposite thing. So let's look that up in scalar.h again. I think it's called get, convert scalar to byte array, right? It's that one. So scalar get b32. Now b32 is exig n6 times 32 and s value.
Yes.
Something like this. Okay. This should reflect our pseudocode. Not exactly, because we have one more hash invocation, right? We hash the z values a little bit different, because we first hash these values into one intermediate hash, and then we hash this intermediate hash, which we should also hash.
Oh yes, the mid hash
into this randomizer. Mid hash. Mid hash.
That's basically always okay. You can always, instead of writing all arguments to one hash, you can write part of it to a different hash and then write the resulting hash to the outer hash. It's just maybe the performance may be a little bit different, but security wise, that's always possible.
Yeah. And I'm adding a to-do here. To-do use tagged hash. Use actual tagged hash.
Yeah. And maybe add a to-do for the mid state, because this would be nicer.
Copy mid state instead of having this mid hash.
I think
that's what it's saying. To do copy mid state instead of computing intermediate hash. Yep, would be nicer. Okay. Trying to compile this now. Okay, a couple of errors as expected. We have this weird thing with n messages right now. So this is n messages, and position 3 of course cannot be null. So we need here 4 and 5. Sig undeclared. That should probably be 664 then. Incompatible type. We need to get its address. Unused variable si. Yep, we don't need it here, but we need it here. Makes pointer from integer without a cast. Yeah, because we need to take its address. Yeah, we need to do this, and makes pointer from integer without a cast, so we need to take the address here too. And here we need to take the address. Unused parameters ctx. Yep. That may be. Do we have other significant errors? Doesn't look like it. Compilation exited abnormally, so we may have some error. Too few arguments to function. So here n
that sounds wrong.
And here we have n6. Okay, it's building, and we can run the test and see what happens. So at least this check here should not fail. And then we're going to proceed with Aggverify. If that works, so I'm going to copy over the pseudocode. And I think this time we start with arg checks. So we have the verify check for CTX. So we want that not to be null. And then we can basically arg check all the other arguments. We don't want them to be null. So for MSG, we do that for pubkey, we do that for exig. And that is it. Okay, our aggregation function failed. Test condition failed, schnorsig aggregate. I know why. Or one reason is here our exig, because we just set it to 1 and wanted to check what happens. So we can set it to 32 times n6 plus 1. This should be the correct size. Okay, in the meantime, we can do this here. We need to compute the randomizers again, and for that we need to parse every signature. So let's first try to compute the randomizers. Perhaps we can copy, we should abstract it better, but perhaps we can just copy some code for now. Actually, I think we can just copy this into a function. because this computes our mid hash. Should be the same for both. But not really, because here we want to do more in this loop. Okay, now the error is in aggverify. Okay, so our aggregate function at least did not immediately fail, but that doesn't mean it's correct.
Yeah.
So
Which check fails?
819. Line 819. That's here. The aggverify check.
Yeah, we currently call return just 0, I guess.
Yep.
Right? Yeah, okay. Right then. It's expected then.
Yeah. Okay. I'm wondering, where do we store the public keys? We don't want to use multi-exp, so we can have multiple loops. So we should first compute the mid hash again. So I'm going to write a function for that. I think that's the way to do it. Right. So I'm just copying this over. We call this int compute. It's a static int because we don't want to export this anyway. It's only used in this file. We call it compute mid hash. And in the end, we return 1. And this. And then our arguments are basically similar to the arguments here. Don't need x and x size, but we need these. And an out argument, which is simply our mid hash. Okay, so let's compute that mid hash in this function. If compute mid hash fails, then we return 0. We don't need that. Let's see if that works. Oh, we need to remove that. Compile project. Okay, bunch of errors. I undeclared, CTX undeclared. Okay, and the rest I think is unrelated. So we need some CTX here. And we need some UN32T I.
Maybe put the context first.
Right.
Just by convention.
So compute mid hash gets a CTX argument. Let's see if that works. Unused parameter. Okay, we don't care about this error. So that looks good. So now we can compute this mid hash here as well. Unsigned char mid hash. It's 32 bytes, and we just copy it a bit smaller. Just copy Where is it? Here, aggregate, compute mid hash. The arm should be similar, except that we don't have N6. It's called N messages here. Then we return 0. Okay, now we need another loop to compute, to finalize these randomizer values and also multiply them with these equations here. For I, we need some I value. I is equal to 0. I is smaller than n messages here.
Yeah, maybe we should get the types right at some point, because we take size t's as parameters, but then use fixed size integers.
Okay, the easiest way to fix this is to just say, well,
Yep,
we only have 32 many messages, and here.
Yes.
And we need to do the same in the include file.
Yeah, that will be enough for everyone. Or, no, I don't know. I guess.
Should be.
Yeah.
All right. Okay, so now we iterate over this and we need to finalize the z value. Perhaps we can we just write a function for that? Well, we could. We probably should. But I'm going to copy this over. So we take the mid hash and we hash it with I, and this is our randomizer. We don't have SIs anymore, just have one combined S. And okay, we have our randomizers now, and now we want to compute this part. And let's see. Let's see. Perhaps let's start with Ri, which let me call. So these are not scalars now. As you can see below, Ri is a point, and we basically interpret this byte value as an x-coordinate. And a point in libsecp is represented by the type GE, group element, right? And we call this R value, I call it RP for R point. And yeah, that's the, here you see the struct for a group element is just an x coordinate, a y coordinate, and a flag, whether this represents the point at infinity. Okay, so we have a 32-byte R value. We now need to get it into a group element. So how can we do that? I suppose we don't have do we have a smart function to do that for us? Set equal to the point with a given x coordinate and a y coordinate is a quadratic residue modulo p. I think that's what we want. We can look into
Schnorr
function. We can look into the Schnorr function, how we do it in the Schnorr function. And so as you have maybe seen here, the x and y coordinate of a group element are FEs, field elements. So since our R value represents a field element, we're going to first parse this as a field element. And then what happens with this field element? Oh, here we just check whether it's... So that's not enough, actually.
No, but we pass it into R. Right?
We don't...
Somewhere.
Do we?
I know
I don't think so. We compute it. But what we could also check is in extra keys main impl, how do we parse X-only pub keys? Because that's basically the same. Yep. We just need these two functions. Where's our loop? Ah, here. Okay, I'm copying this over because that's what we're doing right now. Rx. So we have this field element Rx and we parse it from X sig I times 32. And we should check the exig size again. So that should actually be the same check as before. Because if the exig is too small, of course, we cannot verify it.
Yeah, we can also check the for inequality, right? I mean, if it's too large, it's also invalid.
Is it?
Yeah. Because we want a canonical encoding.
Okay. Then, so we have the Rx value, and then we basically set a point to create a point with that particular x coordinate. What is that, 0? That means on, okay, whatever. So that should be fine. So we have our R point. It's now in RP. What else? We need this. And we need this public key.
Yeah, for the key, it's basically the same.
For the key, it should be basically the same. So we have Rx, perhaps we can call this Px, point, and then PP, pub key point. And we can simply copy this. Perhaps we should also abstract it into a function. Not really, perhaps. No, actually, that's wrong because our pub keys are already in the X-only pub key type. They are not represented as bytes. So what we need to do is...
Indeed. Yeah.
Let's look into the extra keys.
So the pseudocode is not...
again.
The pseudocode is not accurate here. We expect the user to parse the keys first.
It is not. It is accurate in the sense that this is how it would appear in a BIP, perhaps. But
yeah,
in SegP we already have it basically parsed, because parsing takes time because you need to recreate that point. So if you want to, let's say, if you have multiple signatures created with the same X-only public key, then you don't want to parse the same public key all the time because it just takes time.
Yep. And this is why we have a pub key parse function in the library that the user needs to call first.
Okay, so what we need is this X-only pub key load function, which takes a pub key, an X-only pub key, which is this is a public type, user-facing type, and extracts the group element, the point, from it.
Essentially, this function does nothing. It just converts from a user-facing type to an internal type.
Yep. takes a CTX. So I suppose it can fail. So we need to check that it doesn't.
Really? Can you check?
I think it fails if the pub key is all zeroed.
Oh, yeah.
So we write the result in PP, and our pub key is pub key I. Turn 0. Yeah, not really, but anyway. Comment isn't really accurate. And we don't need PX anymore.
Is this an arc check if this fails? I'm not sure. Probably not. Guess we would need to look this up, how we handle
it. Just calls pubkey load and pubkey load arc checks.
So in fact, this actually won't fail. It will always return 1, but it might die before it
No,
returns 1.
arc check returns 0, right? So if it doesn't die.
Oh yeah. Okay, right, sure. It's hidden in the macro, yeah.
Okay, so now we need to recreate this challenge hash, and I think we already have a function in schnorsig verify and sign to do that for us, and it's called schnorsig challenge. I think we just need to call that. Okay, what does it require? We want a scalar e. Easy. That I scalar ei. And we want. Oops.
Maybe just call it E. Yeah, I mean, doesn't matter, but we usually don't have the I's there in the code.
Because we usually don't have.
Oh, we also have set I. Whatever. Okay.
Yeah. Okay, so this is our a 32-byte, I suppose. Yep, 32-byte R value, and this is in exig I times 32. And we have a message I. And we have unsigned char pub key, so we actually need to serialize the pub key again. PK sir. We already did that above, so we can just do the same thing. I thought we did that somewhere. Oh, we have to do it twice now. That's not very nice, because we now do it in compute mid hash and do it here.
Yeah.
That's the wrong function that
can
I copied.
Can be done nicer.
Here, that's the one.
In general, it's writing crypto code can sometimes be strange, because like if you write the signing function and the verification function, for example, there's a lot of code duplication, but it's sometimes also hard to extract it into helper functions, because yeah, for example, error handling is a little bit different, and you need to care about constant time implementations and stuff like this. So we tend to copy and paste code quite often, and may look strange, but sometimes it's the nicest thing.
Yeah. I think we could polish this code quite a bit more.
Yeah, of course. Yeah, this is far from perfect, and don't use this. This is the first draft
to do here. Compute pubkey serialization again after mid hash.
Yeah, this can be done better.
Okay, so we have the challenge. So essentially, I think we have all 3 components of this. So plus the Z value. Okay, and what we can do, how do we do this? So what we want to compute is this for now. So we need some EC multiplication or scalar multiplication, and for that there is this header file ecmult.h. And there are multiple ecmults.
Yeah.
So I think we need this one.
Yep.
Because this allows us to multiply with an arbitrary group element A. There's also ecmult_gen, which allows us to only multiply with the generator. And there is ecmult_const.
Yeah. So maybe let's first explain the difference here between the first two. It's not only in their interface and their functionality, but also in their constant time guarantees.
Yep.
So the ecmult_gen function is what we use under the hood for key generation, and the value A here is a secret. It's usually a secret key, and we also use it during signing, for example, to generate the nonce and so on. So it makes sure not to leak data about the scalar A here via timing channels. Whereas in our case now we are in a verification function, so there are no secret values, so we don't bother. We can use the other function.
Yep.
But there's also a constant time function that multiplies secret scalars with arbitrary public points, and this is the one that you mentioned in the ecmult_const module, and this is used in ECDH for key exchange.
Yep. Okay, so let's do this. I should also perhaps... okay, so CTX, then the output is set to R, I think.
Yeah.
So
almost all of those number theory functions, like the group functions and the field functions, and all of this usually is written in this assembly style parameter order. So the first argument is the context, but after that the first argument is the output, and the other arguments are the inputs.
Yep. Exactly. So this I'm going to skip for now, but here is our scalar, and our scalar is zi, because we're starting with this multiplication, zi times ri. I think doesn't really matter how we do this, right? In terms of multiplications, if we do this.
I think with one way you could save one, not ecmult, but a scalar mult, which is super cheap, but
yeah,
could optimize for it, I think. So I think if you compute it as it's written here, then you save one scalar multiplication. Of course, that's rather stupid, because the best way to do this would be a multi-multiplication,
yeah.
and then this form wouldn't be ideal. So we have also a module that allows you to compute what we call a multiplication, so a lot of terms with it's the sum of products. But we don't do this here because this would be beyond the scope of this video, I'd say.
Yep. But perhaps it may even be easier API-wise.
Maybe, yeah.
Anyway, but let's try it like this for now.
Also, the savings wouldn't be large here because it's just two just the sum of two products, right? Those multiplications really show off if you, I don't know, have n points or n products.
Yeah. Okay, so EI, so we're going to do this first. EI times PI. So EI is our scalar, and we have no scalar for G, because what EC mult actually does, if you give it an argument here, it adds to whatever else you're computing, it adds ng times the generator. But since we don't care about the generator here, I'm going to try to set this to null.
Yeah,
and
I'm pretty sure that works. So.
Yeah. And okay, we have EI, and now we need this. So this is a Jacobian group element, and so far, or a group element in Jacobian coordinates. Right now, we only have normal group elements. Just in short, what is it? If you look at the definition of GEJ, looks very similar. It has x coordinate, it has a y coordinate, but it now also has a z coordinate. And the point of this is that you can use these group elements in Jacobian coordinates and do some further computations with it, and only in the end, when you want to serialize the point, you can compute to the other format, which we sometimes call a fine format. And this can save you some time. So converting a normal group element into a Jacobian group element is fast. The other way around is rather slow.
So yeah, so it's just a different, faster representation of group points that we may use in terms of.
Yep. So the function, I think, is called GJ set GE.
Yep.
Let's see.
Yeah. By the way, you can show what it does. It's super simple.
Yeah.
It just sets x to x, y to y, and z to 1.
Yep.
No. This is why conversion is fast in that direction.
Okay, so let's call this PPJ. That's our point in Jacobian coordinates, and P.
Yeah. Right, and now it's in a forward such that we can use it in the EC mult function.
Yep, I'm going to add another.
Yeah.
So that's PPJ, and I use another group element ACK for accumulator. That's going to have our, or perhaps call it, call it accumulator.
Oh.
Okay, so we've done that. We have EI times P. Now we need to add these two things. And there should be a function for that. GEJ add GEJ.
Yeah, is the second one a J already, or
not
can
yet?
We just? I think we can just add the GA. Yeah, right.
Yep. So that's that one. GEJ add GE. Okay. So GEJ add GE. We have ACK.
And we add the R1, which we call here.
We add ACK. ACK is set to ACK plus RP.
Yes.
And now we need to multiply the whole thing. So ACK with ZI. Okay.
Yes.
And the result we add to our overall sum. This is going to be our sum. I'm going to add a new element for that.
Can you show the pseudocode again?
Yep.
Right. Yeah. Let's make a new element for that. That's why it's weird to call the other thing accumulator, maybe, but
yeah,
it depends on how.
We call it accumulator ECI.
Yeah.
Group.h. So I wanted to check here what kind of addition function we have. We have GEJ add var.
If you find a function that has a var suffix, it always means variable time.
Yeah.
So it's
so
it's
we
not
can
constant time.
even add ge var.
Var, yeah.
It's faster,
yep.
presumably.
Yeah. But unfortunately, the other direction is not true. So if there's no var suffix, it doesn't mean that it's constant time. Then you need to read the docs.
Okay, we want our sum again, our outer sum. Let's call it outer Ag. That's going to be a point in Jacobian again. So let's call it outer.
Yep.
Or outer sum to distinguish it even more. We need to set outer sum to 0 or infinity, however you want to call it. So I'm looking for that function.
Yeah.
Set inf.
It's strange in EC groups that the neutral element is often called infinity, but then you write it 0, right? So 0 and infinity are probably the most different things you can imagine. Yeah. In this case, it's just a synonym.
Set infinity outer sum. And then we gj add gj var. I think that thing exists. No?
Gj. Yep. Should be.
Add gj? No? Nothing's wrong.
Maybe not.
gj add.
Add var.
Add var.
Yeah, right. Yeah. It doesn't.
Okay, that makes
have
sense.
The
and
thing.
We have outer sum plus outer sum is equal to outer sum plus Ag. And there's another argument which we don't care about.
Really? What's that?
That's RZR.
Oh yeah, there's some. Yeah.
It's
used in some specialized function.
Yeah.
We don't need this here.
Okay, we have the outer sum, and now we can compute S times G. And for that we use EC_mult gen? No, we use the same EC_mult, I think.
Yeah, we shouldn't need the gen here.
So we use EC_mult. We set SG. We need some new variable.
You could reuse
left-hand
the
side.
Okay, yeah, right. Okay, yeah.
Left-hand side, and here we don't need a group element, so we could call one this left-hand side here and 0 or inf 0 0 0, and here we want S. Okay, first problem, we don't have an S yet. So let's declare that here, sec p to 56k1, scalar S. And we already did that here. Set B32 is what we need. S, Ag, sig, N messages times 32.
Yep.
And do we care about overflow?
Yes.
Apparently not.
I think we do, to make sure we have a unique representation in the signature now, because we are parsing S now from the signature.
Yeah, we already fail for single verification. Okay, that's right.
Note that we didn't care in the aggregate function, because this is, well, I mean, the function is supposed to take valid signatures and output a valid aggregate signature. If you give it invalid signatures, you don't guarantee anything. Yeah.
So if overflow is set, then we return 0. We need to define this overflow variable. So int overflow equals 0.
Maybe don't initialize it there.
Are you sure?
Yeah, it's in it. It will always be initialized.
Okay.
And then our tracking is better. Here we initialize it. Pretty sure it's initialized by the set function.
If overflow overflows over, okay.
Yeah. This just this improves static analysis because then we make sure that this value is always written. But it's really a minor thing.
Okay, we have S. We have S here. We need this left-hand side. Let's replace outer sum with right-hand side. Huh? That's cool, all right. Outer sum, right-hand side.
Nice, yeah.
And then we naturally have a left-hand side.
Yep.
And this left-hand side is here. And now we somehow need to tell ECMult to not do any multiplication here. I don't think that works.
Yeah, I think that doesn't work.
Would be nice if it would work. Perhaps if we said, is this the right one? If we said what do NA? If we set NA to 0,
now you.
Yes,
okay.
then it should work. So we need some 0.
Scalar.
0
That's
scalar.
easy. Yeah, it's just a constant. But maybe you even have it in the module. No, I'm not sure. The scalar module.
Scalar H 0. Could be.
In the other function. But I might be wrong. Sorry, in the other file, in the implementation file.
Scalar impl.
There it is.
There it is. Nice.
Scalar 1.
Scalar 0.
Yeah, sorry. Sure.
Okay.
Yeah, which saves those 2 instructions probably. But okay. It's nicer code.
Okay, so we've computed S times G now, hopefully, and now we need to subtract the left-hand side from the right-hand side and check whether the result is infinity.
Right, because we don't have a equality function for group elements, but we don't need one because we have subtraction.
56.
And check for we have
neg
equals 0 function.
So we now negate the left-hand side. That should work, and then we can GJ add var.
Sorry, yeah, we add the right-hand side to it.
Left-hand side, right-hand side, and then we check GJ is infinity.
Do we have this, or do we have to convert first? I think we have it for.
We have it.
Yeah. Oh yeah, sure. It's easy to implement.
Ooh, okay. Yeah. Is that it?
Yeah, I guess. I mean, I'm sure it will have a bug. But...
Unknown type. Include. stdlib?
Standard int and
std
the other in brackets.
Of course.
Maybe also include. Yeah, okay, not here. Yeah, in the implementation file, we could also include then a string because we use one copy.
Right.
Maybe it's already there.
664 is undeclared. Because we don't have. Okay,
I think it's undeclared in the caller, not here.
Yeah. Right, but for good reason. I'm trying to figure out how to change this. We call this egg. I don't know how to do it because they're at different places, right? In the aggregate verify, we don't have individual signatures.
Oh, yeah. That means we can either create pointers to them, which is weird, or we can just still copy and paste the code and modify it for now.
Or we provide a callback how to extract the R value from a.
Yeah. We could do this, but wouldn't do this as a first step now, because it's probably another source of potential mistakes.
I have an idea. How about this? So
Yeah.
one of them is
null.
We can arc check this.
Yeah, we just don't. I think we want to verify check here because it's not a user call. Now the problem is, what if both are not null?
Yeah. That is a problem. If 664 is
it's okay for now. It can be cleaned up.
Else.
Yeah. Yes. That should. Do we have N6 there? Yeah. That should do it. But it's really ugly.
It's not as. I mean, there's no much better way to do this, I think.
Yeah, I mean the other way is even more ugly. I guess we would now write two wrapper functions, right, that don't take the null argument.
Yeah.
But apart from that, it's probably okay.
I need to take the address of this. Hash undeclared. Yeah. Just don't declare it. Do we need it somewhere else? No, we just need it inside of this loop. Okay, this. What else do we have here? Expected That we already
But maybe
fixed.
that's the same. Yeah.
Here we have the problem that we want CTX EC mult CTX or something. Because it wants the specific EC mult context. Do you have EC mult somewhere here already? EC mult CTX, yep, that's the one. Let's try to compile again. Ooh, still a lot of errors. Oh. Need to take its address. Too few arguments to function gj@gevar. Is that the weird? Yeah, with a weird fourth argument that we don't need. Okay. That's easy. Oh, and again, we need EC mult CTX.
Oh, yeah. Sorry, I missed it. Yeah,
And
there's
probably again below.
Yeah, the context has two subcontexts which just represent data structures for different things we pre-compute, and one of them is just for the ECMAL function, so we just pass that particular one to the ECMAL function. Whoa, no errors.
Yep. Let's see.
Yeah.
If the tests don't fail now,
I'm
we'll
pretty
be
sure
surprised. We
Yeah.
can also do the test hack, which is we comment out everything but our Schnorsig tests.
Yeah, just need to make sure that we keep our we keep the interesting one in.
Yep.
Maybe you should have markers in the code for easier commenting.
Yep.
Test condition failed, yeah.
Okay.
Great.
We remake and then we try with Valgrind.
Yeah, we could also do this.
What else would you suggest?
Yeah, I think it's the best first step. Ask the tool. But I could imagine it's not a memory issue. It's really a bug.
So our test binary takes an argument which is the number of count. It's the number of runs basically. So usually default is 64. If you set it to 1, then the tests will finish faster. And here we already see condition move depends on uninitialized value. Schnorsig egg verify 379. And what is our uninitialized value here? 379. Depends on uninitialized value. What about ZI? ZI is in fact never set anywhere.
Yep.
Why? Where is CI set in the other file? It's set to the randomizer. And do we actually create the randomizer here? Yes.
No.
So we just missed that part.
Oh. Oh, yeah.
Okay, and then it couldn't work.
Was this the right call now? Yeah, we finalized the hash to randomizer. Yeah. Let's hope.
That was it, then it'd be easy. Nope.
Lumping core still doesn't work, and now we don't have a memory issue. Yeah. So we probably want to find out at which place it, which of the checks fails. Yeah. Could also use debugger, right? That's okay.
Debugger, I don't have a lot of success with debuggers. Okay, fails at the end.
Really?
Yep.
Sad.
Sad.
That's sad because
That
this
makes
is
it
basically
especially
the
hard.
entire function, yeah.
Okay, so we could try to abstract a little bit more. So that's what I usually do. So one thing that we could abstract is this ZI computation that we already messed up. I don't think it will help much because we already basically checked that those are the same. So we could go through the code again. What does it do? Assuming everything is right, it multiplies the SI values with ZI, adds them up to S, and then stores S in the end, and it also copies the R values into the aggregate signature. So I think that looks good, at least.
Do we copy the S value? Yeah, in the end, yeah.
Yeah.
Get it.
Okay, here most likely something's wrong here in these computations because it looks quite difficult to understand. Let's see our Schnorsig challenge. Is that correct? Schnorsig challenge takes R value I, takes message I, takes the serialized pub key. Serialized pub key is pub key I. So that should work. Then we said PPJ is the pub key point, and we multiply the pub key point by EI. So compute that thing.
Yeah.
And then we compute that thing essentially. So we add ACK, which is EI times PI, to RP. And then we multiply the whole thing with ZI. Which seems right. And then we add this accumulator to our right-hand side. And our right-hand side is initialized to 0 or infinity? Yes, it is. Okay. Then we obtain the S value. We multiply the S value with G, store the result in LHS. We negate the left-hand side. We add the right-hand side to the left-hand side. And then we check whether the left-hand side is infinity. Okay. Yeah.
Yeah, I have no idea.
Work. It should work. Okay.
You could check the mid hashes.
Yeah. Could
Compare
start
them.
checking the mid hashes, or the randomizer even.
Yeah.
Rand.
Nice.
So the randomizer
Yeah,
I is rand 0.
2 integers will be enough. Yeah.
And the same.
No, but you should pass 2 values, right? Oh, you give it I. Yeah. Just one integer.
It's neither now. Randomizer. It's called.
But we also want to print it in the. Yeah, okay, sorry, yeah, you did it.
That's going to be super boring to the audience.
Yeah, debugging is. boring, of course.
That's why you shouldn't make mistakes in the first place. Okay, ran 0. The randomizers are different. That's already a good indication. But I don't see why.
Yeah, I mean, maybe it's in our strange function with the two nulls.
Compute mesh
take the
CTX
wrong
mid
values.
hash, MSG32, pubkey and messages and 6. Okay, that looks fine for me. Let's look into the actual function, not only how it's called. Can we XOR this?
Yeah, we can. The right operation here is not equal. So you can. Yeah, you just need to add brackets now.
Yeah.
It looks strange, but it's.
Yeah, that's a good one.
It's the right one.
Okay, let's run the test.
But
in
I
the
think that's not the
That's
issue.
not the issue, but still.
So here is this the right?
That's wrong. N6 is wrong. It should be 32.
Yeah.
But why doesn't Valgrind detect this? We should run with
Because-
address sanitizer.
No, because NSEG is smaller than 32.
That's
so
right.
It's fine. Yeah.
Ha!
Oh.
Okay.
There it
So
is.
our tests pass. This could mean that our code is relatively correct, but it doesn't have to mean that.
Yeah. Yeah.
You can only verify
Neither does
this.
it. Yeah.
Yeah, by
Neither does it
careful
mean it's secure,
inspection.
right?
Yeah.
It's even worse. That's so bad about crypto code. You can write code that passes all tests, and it's still insecure because you can't write a security test.
Yeah. Exactly. Let's look at the tests again. What do? We aggregate it and we verify it. But we only did this once and only for 3 different signatures, but they're all randomized. We could do this a couple of times more, but it probably won't make a difference. We could wrap this in a loop. We could extend the tests in many possible ways, but I don't think we have to do that.
Yeah,
right
we
now.
can clean up the mid states function, and I'm sure we can clean up other stuff.
Yeah, I left a few to-dos here. And again, if we go into our bonus stuff, we definitely want some kind of unforgeability tests in quote.
Yeah, I mean it's at most a sanity check, but it's certainly a test we want to add.
It means it would mean, for example, that all the values are properly hashed into the randomizers.
By the way, like interesting variants of this test. I mean, of course, random bit flipping is not that useful, but you can do it. More interesting things are like negate some group element, for example, or negate some scalar and the signature, and then see if it still passes.
Yep. Although in our case, we have no group elements that could be negated, right?
Yeah.
Because the R's and public keys are only encoded as X only, but I get what you mean.
Right, you got interesting, yeah. I mean, you could at least negate the S, huh?
Yep.
Yeah.
Okay. As I said, like additional things to do would be to move this into a separate module, perhaps more tests, multi-exponentiation. We've talked about this, and also optimize the randomizer.
Streaming API would also be another thing we could do.
Streaming API.
Yeah, for both signing and for both aggregating and verification, right? Where you have like, let's say we have this use case on the Bitcoin blockchain, and you are the miner and you want to create a block, and you get incoming signatures, and when they come in, you stream them into the aggregation API.
Yeah. Right. Although aggregation should be rather cheap.
Yeah.
But
Right.
anyway, because aggregation is just... Does it even work, streaming API, when we have to hash everything that we've seen?
Keep the mid state. Right?
Okay, and then in the end, you do this. So you're only...
Because then
You're only doing this, basically.
Yeah.
When streaming.
Yeah, right.
Okay.
Yeah. I mean, yeah, not entirely. I mean, you can also do some of the multiplications already, right?
No, because you don't have the Z values yet. You only have them in the end.
Oh, indeed.
Yeah. I mean, you could hash into whatever you get. You could also already hash it into this.
Yeah.
Z value into the mid state. Yep. But
you could also, yeah. Oh yeah, we may even want to write a better algorithm. Yeah. So there's a lot of things to think about. Yeah.
Yeah. All right. Cool. Was a good session. Anything else we want to say?
Maybe to wrap up, point out that certainly this is not rocket science. This idea of half aggregation. I mean, we didn't. Of course, this is not a production-ready implementation. But if we manage to implement this in, okay, it's over 2 hours now, but in a little bit less than 3 hours, without extending libsecp too much. So we didn't have to write any new functionality, right, to implement this.
Yep.
Then this means that's pretty easy to implement in the end, and certainly a thing people could be interested in.
Yep. And one reason why that's the case is because it's non-interactive, right? Just take a bunch of signatures, aggregate them.
Right. Yeah.
It's just one function call.
Yeah, this makes things so much easier on every level, even here on the API level, but also for every code that uses this.
Yeah. Right. And what I'm going to do is I'm going to open a pull request with half aggregation.
Yeah. Right. And if you made it through this entire video, and I'm sure you have some comments about the code, then just
right.
First of all, thanks, and second, would be great if you can comment on the PR then.
You stared 2 hours at this code with us.
Yeah.
You might have comments.
Right.
Yeah, would be awesome if you could help us out here. All right then. Guess we wrap it up here. Goodbye. And
Bye.
hope you had some fun. Bye.